your exam is going to be 15 questions. They will be 2 points apiece, and if you explain your justifications, you can earn some partial credit on that. And if we take a look at the first three, it's going to ask you these three things: is what's a particular array going to look like after 3 iterations of a selection sort or an insertion sort. So the first two, actually. That's these questions down here, that you're going to be given something like this and be asked to predict what the iterations are after 3 times through using the selection sort for question number 1. And question 2 is what it would look like after 3 iterations if you were doing an insertion sort. So I created a Word document to try to explain this just a little bit, and let's just kind of take a look at that. And what I did was I copied over those questions and I put the original array here and then traced the algorithm, so to speak. So on a selection sort goes through and it finds the smallest number first. So it's going to find this 5, and then it does a swap. It swaps it with the first index. So the 5 and the 63 get switched on the first iteration. Now the 5 is in the correct position, so the algorithm continues and it starts looking from 19, from index 1, which is at 19, all the way through the rest, and it finds the next smallest, which is 15. So then it swaps 15 with 19 on the second iteration, and then on the third iteration it starts looking at 19 and looks at the rest of these, and as we're looking, it starts on index 2, which has a value of 25. It goes through all of the rest and it finds that the smallest value was 19, so then it swaps 19 and 25. So on the third iteration the values will be 5, 15, 19, 25, 75, 24, and 63. So if we go over and look, that's going to match up with D, as in dog. Now the other thing to note about the selection sort is there are 1, 2, 3, 4, 5, 6, 7 elements, and so the number of passes, or the number of iterations, the maximum number of iterations, is always going to be 1 less than the number of elements. So we would know that after 6 iterations the array would be sorted. And that is true in a selection sort as well as in an insertion sort. Okay, the second one is an insertion sort, and so just taking a look at the algorithm there, after I stop messing up my screen here. So this next example is an insertion sort. On the insertion sort, when you take a look at the data items here, and there's 1, 2, 3, 4, 5, 6, 7. So again, after 6 iterations the array would be sorted. It's always 1 less than the number of elements on the selection and on the insertion sort. And both of those are an n squared big O notation. But when you do an insertion sort, it automatically starts at the second element, which would be index 1, and it looks to see if this value is less than or greater than, depending on whether you search high to low or low to high, it looks to see whether this item is in the correct, or it takes 2 and it inserts 2 into the correct position. So it's going to compare 2 with 19. Is 2 smaller than 19? Yes, so 2 gets inserted into the correct position and 19 gets shoved down to the right. So now I am looking at index 2, which is number 1, and I go back all the way to the beginning and I compare it with the first item, which is 2. Is 1 less than 2? Yes, so it inserts 1 to the correct position and it slides 2 and 19 down. 2 and 19 get slid down. So on the second iteration, the 2 items are in position. And then it looks at the number 12. and 12 goes all the way back and starts comparing itself to 1. Or is 12 less than 1? Nope. Is 12 less than 2? Nope. Is 12 less than 19? Yes. So then it inserts 12 into the correct position and 19 gets slid down. If for some reason I had to, when I go back and I insert, it's going to keep moving all of these elements down as needed. But now after the third iteration, the first 3 items are in the correct position, and I would continue through this until I had 6 iterations to make sure that it was in the correct order. That is the insertion sort. The next question that we are going to take a look at is going to be number 3 on the review sheet, and that's going to correspond up here with our review. It's going to be finding, if I take a look, something like this. Given a merge sort, determine how many calls in the method are required to completely sort an array. Giving a sorted array and a target, determine how many comparisons are necessary using a binary search. And so those are the items, 11 and 12 are kind of what we're looking at here. So if I scroll down and we look at question number 3. This one I referred to on the previous video, and it says consider the sorted array of integers. And so we know that they are in order. It says if 518 is the target value for a binary search, how many iterations are necessary? So it is looking for this 518, and it wants to know using the binary search, which is a divide and conquer. So you divide in half, decide whether the value is lower or higher than your target, and keep doing that algorithm until you find it. We are going to talk through this quite a bit because there's several other examples kind of like this that you can practice in the other review packets or the other review links that you have. But I am going to step through this one in quite a bit of detail. So if I go back to my work, the first thing that we want to understand is that when it's a divide and conquer algorithm like this, we can use that base 2 or powers of 2. So your powers of 2 from 2 to the 1st through 2 to the 10th are here. 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, etc. 2 to the 10th is used frequently to do some approximations, and it is 1024, but we just say it's approximately 1000. So keep that in the back of your mind. The base 2 logarithm of these, if I were to evaluate, for example, if I put it in logarithmic form, base 2 log of 2 is 1, base 2 log of 4 is 2, base 2 log of 8 is 3, etc. This corresponds with the number of iterations for x elements, and that x number of elements is the right hand side over here on your powers of 2. So if I had 500 elements, it would take me approximately 9 iterations in order to find my target. So on this question number 3 that's over here on the left, and it's asking how many iterations, the first thing is it's asking specifically how many iterations to find the 518. So we're going to use the algorithm, which is you take the low index plus the high index, divide it by 2, integer division, and some of them I've calculated exactly, some of them I haven't. But because it's integer division, it's always going to truncate. So here's what's going to happen. Our low index is 0, our high index is 99, divide that by 42, we get 49. So then I look to see where the 49th index would be, and it would be somewhere in here. Okay, and so my target value of 518 is above index 49, so now I move my low value up to 50. Because it's not 49, I go one more, so I now have a new low value of 50. Do that calculation again. 50 plus 99 divided by 2 is 74, and so 74 is somewhere between these two values, and so 518 is below the index of 74. I now have a new high value of 73. So I go down one less, and I do the calculations again. So 50 plus 73, index turns to be out 61. It's 61.5, but we truncated to 61. 61 is somewhere between these two values, and so my target is below 61. So I now have a new high, excuse me, so I have a new high of, it should be 60 actually, because I need to go down one. So if I do that calculation, then 50 plus 60 is going to be 55. It's not going to be 55.5. And then my target is hit on the 4th iteration. So the answer to question number 3 is 4. It occurs on the 4th iteration. However, what if I change the question? And that's kind of like this question down here on number 4, but I'm going to use number 3 to answer it. I'm going to say, if a binary search is performed, how many iterations are required to determine that a number is not on the list? So if I go back to my work and I say, what if we change the question? And so I'm going to change the question to, what if the element was not on the list? How many iterations would occur? So we're going to say that the target is somewhere above the 50th index and below the 61st. So we're going to kind of continue with our work that we had here. So we're going to redo this 4th iteration. And I'm going to say the target is above 55. So I have a new low of 56. And my calculations are going to be slightly off there because I did this calculation up here wrong, but you get the idea that you take the low plus the high index, divide by 2, and if you calculate it all the way through, you're going to get to the 7th iteration. And we kind of should have known that, because how many elements did we have? If we go back here, I had 100 elements. And if I go all the way back up here, what happens if I have 100 elements? That means it's got to be somewhere between the 6th and the 7th iteration. The 6th and the 7th iteration. And because they actually, and so in order to actually answer this question accurately, I should redo my calculations down here, because it might be 6, just 6, but I believe it's going to be 7, because I don't get to my 100th element until I'm past the 6th power, so it should be 7 iterations. Okay, so let me go ahead and calculate those. Okay, I redid my calculations and it actually ended up with 6 iterations, because on that last one we get an index of 59. If I say the target is below 59, I now have a new high of 58, but that's less than my new low that I had on the previous execution. So therefore, the algorithm quits. And so here's the deal. You're going to get asked questions like that. And I want you to try number 4 on your own, and I will post the answer to it. And so chances are you're not going to have that close of a distinction between the iterations. It's going to be usually actually a lot larger numbers that they're going to ask you on questions like that, and I'll give you some more examples when we go through some of the other review pages. But this particular video shows you a couple of things. Number one, you can do this algorithm, low plus high divide by 2, low plus high divide by 2. It's an awful lot of work though. And so the reason that I wanted to show you this power of 2 trick, or the base 2 logarithm trick, is that you can get a quick ballpark. You know it's got to be between 6 and 7 iterations. And so the choices that you're going to pick, generally they're not going to be like right next to each other. This was asking a different question, remember? So generally we'll have a wider, like down here, the options are 1, 4, 5, and 7. So there aren't any iterations that are like right next to each other. You're going to have a better idea just by doing some estimations here as to what that number of iterations are going to be using a base 2 logarithm. And then it also reviewed your selection sort and your insertion sort. And so go online, watch the videos on, there's tons of them out there, but you do have to know how to calculate the first 3 iterations of both of these algorithms. The last thing I will mention on this particular video is the things that we didn't talk about over here. I'm briefly going to go through some of the other review questions on another video, so you guys have that. But why are the merge sort and quick sort better than the selection and insertion? And that goes back to your big O. They're much more efficient. Okay, it's not because the code is shorter. The code is actually longer. It's not because it takes up less memory. It's because they're faster. Be able to identify or rewrite one of the 6 algorithms, and I already kind of talked about that or alluded to that. So you should be able to go low to high, high to low, or recognize whether it is a sort or a select or a search algorithm when you're asked that. What has to be true about a precondition for a binary search is that the data has to be sorted in order. And so the data has to be sorted before you can use a binary search. That's what we call a precondition. We talked about 6, we talked about 7. It says given 3 of the 6 algorithms, be able to list them fastest to slowest. And so you guys, because you get to have your cheat sheet, you should be able to do your big O notation, and you shouldn't have too much problem with that. And under what conditions is a sequential search faster or slower? And again, that would be using your big O notation and comparing worst case and best case scenarios. So make sure that you have that on your cheat sheet. Which of the 6 algorithms is a divide and conquer? So any of them that split in half, so like the merge sort, the quick sort, and the binary search are your divide and conquers, okay? And then we've talked about 11 and 12, and then be able to identify or rewrite. We kind of already alluded to that. And then the sequential search I gave you uses a for loop, be able to rewrite it using a while loop. So, and be sure to understand that if you're using a while loop, you always have to check to see if you are at the end of the array before you do your comparisons, because if you don't want to go outside of array bounds, okay? And then what criteria should be used when choosing a sorting algorithm? That deals with, you should use speed, you should use the how much memory it's going to take up, and the length of the array, I believe. There's actually a question I think that deals with that, okay? Here's an example of ordering low to high and seeing if you can match up the correct things, but then you should be able to put these also in order from low to high. And then this is going to be your free response question here. And so make sure that you kind of study that. You don't have to know the specific coding right here. What you need to understand, or what we are comparing, is what's better. If I want to go through a large set of data, okay, in a 10,000 digit array, is it better for me to do a sequential search or do a quick sort followed by a binary search? In other words, should I just start at the beginning and look for whatever I'm looking for, or should I sort it first and then do a binary search? So use your big O notation and use the 10,000 as a value of n, like you would do 10,000 squared, or you would do log of 10,000. And you can use a base 2 or base 10 as long as you keep it consistent, okay? Base 2 is probably preferred, but you can use base 10 on your calculator if you're not sure how to punch in base 2, and you'll get a comparable results, okay? So make sure that you study that, email or ask questions on that if you need to, okay? You do not have to do, again, any of these actual assignments.